Yeah, I gotta do it today. It's the first homework due in my class too. It's funny how you have to train them too. Do that. The first day and they want that.
Okay. So the topic of today's class is matroids in terms of bases. So what do I mean by this? Well, what I mean is that in the definition that I gave of a matroid, I said, okay, a matroid is a set and a collection of independent sets. And so according to that definition, independent sets are kind of the important thing. But from other points of view, sometimes bases are more important than independent sets. And so what I want to talk about today is how you can talk about a matroid only in terms of its basis. Okay. And I'm going to spend the whole hour stating a theorem. Stating and proving a theorem. Which says this: let E be a finite set and B be a collection of subsets. Okay. And the question we're going to address is, how do you know if this collection that I gave you is the collection of bases of a matroid or not? Okay. Then the theorem is this: B is the collection of bases of a matroid if and only if two conditions hold. The first condition is, it's called B1, and it's just as trivial as condition 1 for independent sets. We're just going to say that there's at least one basis. In other words, that the collection of bases is not empty. You must have at least one basis. And the second condition, which is called the basis exchange axiom, is going to be similar to the independence exchange axiom. And it says if you have two bases, A and B, and an element which is in A but not in B, then basically the point is you can swap the element A with an element from B and still get a basis. So there exists an element which is in B and not in A, such that if you start with your basis A, you remove the element A and you add this element B, what you get is a basis. So again, this first thing is kind of trivial, and the basis exchange axiom says if you have two bases, then you can exchange any element of the first one with some element of the second one and still be a basis. you exchange the element A for the element B.
Oh.
Questions?
I can't read that last line. Is that A minus little a?
Yeah, so let me rewrite that again. Such that big A minus little a union little b is a base. What was your question, Jason?
So you haven't said anything about them having the same cardinality yet. Is that a consequence of the second condition, or is that meant to be assumed?
If this theorem is true,
Yeah.
then it must be a consequence.
Yeah.
It must be a consequence of these axioms that all the sets in B have the same size.
We're going to prove that? Yeah.
We're going to prove that.
I think they actually have to, because in order for this basis exchange axiom to work, you take one thing out, add something else in, and that's also in there. So if either A or B if they had different sizes, that would never work.
Well, just
So Chris's comment is this, that basically if you look at these exchanges, you start with A, and if you exchange A for B, then this new basis has the same size. The basis A has the same size as A minus A union B. And you might think, okay, that means immediately that the bases have the same size, but you have to be a little bit careful, because we do not know that you can get from any basis to any other basis using these exchanges.
Yeah, you need to know that there is an A and A minus B too, because that condition doesn't. It just says if you have one of these, then you can do this. So
I mean, I'm going to show to you why it's a consequence, and you're going to see that it's not as trivial as. I mean, I agree with you. It looks kind of clear from this definition. It takes a little bit of work. I wouldn't say it's very difficult, but it takes work. Okay. So that's the theorem. Okay. This theorem is going to have two parts: an easy part and a difficult part. The easy part is that if you have a matroid, in the way that we defined it, then it satisfies these axioms. You're going to see that's very easy. So first direction is the forward direction. Say that you have a matroid and B is the collection of bases. Okay. We need to show that this collection B satisfies these two axioms. So we need to check. First, axiom 1. There is at least one basis. Well, that's definitely true, because there is at least one independent set. And so that means there's at least one maximal independent set. So this is clear. There's not much to say there. Okay.
Federico?
Yep.
Now M is M a particular matroid? One single matroid?
That's right. M is one single matroid, and I'm going to show that if you started with a matroid, and B is the collection of its bases, then B satisfies these two axioms, which is one direction of the proposition. The next thing I need to show is that if I have B that comes from these two axioms, then there was a matroid that it came from. But the first thing is to check that the bases of any matroid satisfy these two axioms. The first axiom is clear, and the second axiom is not very hard, because you're saying, okay, assume that you have two bases of your matroid M. In fact, let me call this B of M, so that it's clear to you that this B that I'm talking about in this part of the proposition comes from a matroid. So if I take two bases of M, and I take an element of A minus B, then what happens? A is a basis of my matroid, which means that if I remove little a from it, then I get an independent set. A minus A is an independent set of the matroid. B is an independent set of the matroid. And I know that A minus A is smaller than B because A and B have the same size. So if this is true, and A minus A is smaller than B, because we know that if I have a matroid, the bases have the same size. So here I am in a condition where I can use the exchange axiom for independent sets. So I use independence exchange to find an element B, which is in B. B is not in A minus A, and A minus A union B is independent. Right? This is from axiom I3 of a matroid, independence exchange. So what did I just do? I found an independent set A minus A union B. But this set has the size of a basis. All bases have the same size. If this guy has that size, then it has to be a basis. The size of A minus A union B is equal to the size of A, which is the size of all the bases of this matroid.
And that's just definition of basis was the maximal size.
Right,
of the set.
remember how do you know if this guy is a basis? Well, it's a basis if it's independent and nothing containing it is independent. But if this guy has the size of the basis, then anything bigger than it cannot be a basis because all the bases have the same size. Therefore, if this guy has the right size and it's independent, it has to be a basis. So A minus A union B is a basis. What is the last thing I need to check? I wanted to find a B. I wanted to find a little b in B minus A. But you see, B is in B, and it's not in A. So that means I'm done. In other words, the basis exchange axiom follows easily from the independence exchange axiom. That's one direction. Any questions about that direction? Okay. Now, if I want to prove the other direction, then what I have to say is, given a collection B that satisfies these two axioms, I have to prove to you that this is the collection of bases of a matroid. So what I need to do is show you what matroid it is. So suppose B satisfies properties B1 and B2. I have to find a matroid whose bases are these. And we know, I think we know what the matroid is that we need to define. Remember that we said that in a matroid, the independent sets are the subsets of bases. Okay. So if I have this collection that I want to show is the collection of bases of a matroid, then let me just say that I consists of the subsets of these guys, the subsets of the hypothetical bases. So the subsets I such that I is a subset of a basis. And I define this to be my collection of what I want to prove is independent sets. What I need to show now is that this definition really does give me a matroid. Need to check that E comma I is a matroid. Okay. And B will be the set of bases of this matroid. How do you prove that something is a matroid? Well, again, this is the nice thing about matroid theory, that everything is kind of streamlined for you. And if you want to prove something is a matroid, well, you prove the axioms. So first axiom. First axiom is
The empty set.
empty set is independent.
It's definitely.
Yeah.
Empty set is definitely independent,
Right.
right?
It's
Why is it? Because
Contained
Contained
in
it's
every
important.
basis.
It's important that
Right.
B is not empty.
Yeah.
That means there is at least one basis, and the empty set is a subset of that basis. So that's kind of trivial. I2 is this kind of hereditary property of independence, that if you have I in J, I is contained in J, and J is independent, then you have to show that I is independent. Well, this is easy also, because if J is independent, that means that J, by definition, J is a subset of a basis. And if J is a subset of this basis, then I is also. Because I is a subset of J. So I just showed that I is a subset of some basis, and therefore I is independent. And as usual, and as you saw in the homework also, here's where the work is. Exchange axiom. The exchange axiom says that given I and J independent with I smaller than J, there exists a J which is in J and not in I, such that you can add it. I union J is okay. We're going to spend the rest of the hour proving this seemingly simple statement. So proof of I3. I need to do this in 2 steps. Okay? And step 1 is exactly what Jameson and Chris were talking about. Step 1 is that I'm going to show that all the sets in B have the same size. All the sets in B have the same size. This is not immediately obvious from my definition of B. In other words, it's not immediately obvious from B1 and B2. Okay, so this is my first step. How am I going to do it? What I'm going to do is I'm going to pick a basis and then show that all the other ones have the same size as this one. So let A be a basis, and it's going to be convenient to, actually I'm going to call it B. And I could pick any one, so let me pick one that has the smallest size possible. It could be that bases have different sizes as far as we're concerned, as far as we know. So let's pick one that is smallest. So let B be smallest.
Have the smallest
Have,
cardinality.
have smallest size among the sets in B. Let B have minimal size among the sets in B. And I'm going to prove claim is that every other basis has the same size. For a change, instead of using contradiction, I'm going to use induction here. So I'm going to induct on the number of elements in A minus B. So again, remember this is step 1, and so I want to call this step 1A. Okay? I want to try to organize this for you so that you can see it in the notes and look at it and make sense of how it's organized, because it's a long argument. So for step 1, the first thing I'm going to do is do the base case of the induction, which is that A minus B is equal to 0. What does this mean? It means that there are no elements which are in A and are not in B. In other words, what that means is that A is a subset of B.
And B is any other. Oh, B is what we started with, and A is.
B is my basis of minimal size.
And then A is just some other basis.
And A is some other basis, such that A minus B equals 0.
Yeah.
So then
Well, you know, B is a guy of minimal size.
so it has to have the same
A is inside it, and so it can be strictly smaller. So therefore, because B is minimal, that means that A has to equal B. It can't be smaller. I'm sorry?
No.
No. Equal as sets, because it's a subset, and it can't be smaller. So it has to be the same set, and so it's pretty trivial that they have the same cardinality if they're equal. Okay. And this should explain to you why. And this may have seemed artificial to you, to start with a minimal basis. Well, now you see why I did that. It's going to simplify my argument. So 1A is the base case, and that's okay. Okay. And 1B is my inductive step. My inductive step says, suppose it's true for, let's say, A minus B equals K minus 1, and let's prove it for A minus B equals K.
So even though you said you're doing induction, it looks like you're getting ready for a contradiction, right?
No.
No, actually, you'll see that it's going to be very much an inductive argument.
You have a bunch of elements that are in A that are in B.
So
It's not
So let me
gonna
take A and B, which are in the set B. You should question. Go ahead.
In your inductive step, in your inductive hypothesis, it's not the same A, right? It's true for all A. It's just that difference has
Suppose it's true for all A such that A minus B is K minus 1. And I'm going to prove it for all A such that A minus B equals K. Thank you. For all A such that A minus B equal to K. Okay. So let me assume that I have A and B, which are in script B, such that A minus B is equal to K. I want to point out something to you guys that you may not be noticing, which is that I am not calling these things bases because we don't know that they're bases. Okay, so it's going to be a little annoying that I have to say A and B are in script B, but it's not allowed for me to say A and B are bases. So I have to say A and B are in this set B that I'm considering. They're such that A minus B is equal to K. Okay, and I need to show. Okay, so A and B are such that A minus B is equal to K. And we did the case K equals 0, so I can assume that K is greater than or equal to 1. Which means that there's at least one element in there. Okay? And again, the nice thing about this kind of argument is that it's completely streamlined for us. You have two guys in B, and I have an element which is in A and not in B. The next step of my proof is forced upon me. Exchange it, right? Take B and B minus A such that A minus A equals B. It's in my collection B. Okay. Now, what do I want to say? I want to apply the induction hypothesis to A minus A union B and B. Why? Because notice that how many elements are in here and not in here?
K minus 1.
Well, you know, A minus B had K elements. Now, I got rid of A, which was in A minus B. So I lost one. So now I have K minus 1 elements. And I added B,
That's in B.
but B is in B, so that doesn't count. So therefore, this is equal to K minus 1. So if it's in B and it satisfies this, that means I can apply the induction hypothesis. The induction hypothesis says that this guy, A minus A union B, has the same size as B.
But the other thing has the same size.
Well, you know, this guy has the same size as A, because you take one element out, put one back in. So that's my proof. It's tricky. It's not. I mean, I wouldn't necessarily say that it's a very hard proof, but you really have to say something here. And this is only step one. Step one is that I know now that if a collection script B satisfies B1 and B2, then the sets in there have the same size.
So if someone throws you a set of those kind of sets, do people talk about the matroid generated by those things? Well, I mean, yeah, that's what we're proving. So you could look at it.
In practice, people just call it the matroid. I'll say more about that.
Okay.
But kind of the point here is that you can talk about independent sets and say that's a matroid. You can talk about bases and say that's a matroid.
No, but I mean, if
And
you
people are-
just had a bunch of sets that were like equicardinal, then this kind of tells you what extra sets you might have to add in almost to get a matroid. Because maybe the set, you just have a set of equicardinal sets, maybe it's not a basis, but you can kind of classify when it is and when it isn't and have an idea of what you need to do.
I see. So Jameson's question is a little bit different. His point is, if I give you a collection B of sets that maybe they have the same size, but they don't necessarily satisfy these conditions. If you want to form a matroid with these guys, condition B2 is going to demand that you throw other things in there. Okay? And that way you can start with the set, with a collection of sets of the same size, and generate a matroid with that. And that's something you can definitely do, and I don't think I've seen that construction before, actually. I mean, it definitely deserves the name of the matroid generated by this set, but
Yeah.
I don't know what people know about it, and it's something we should definitely think about, I think. Sounds like a very natural construction. Okay, so let's remember where we are. So again, I'm trying to prove that this collection I satisfies axioms I1, I2, and I3. I saw that these two are trivial, and I was in the middle of proving I3. And to prove I3, I said I'm going to need to do two things. The first thing is step 1 over there, and now I'm actually going to do step 2, which is basically to finish it. Step 2. So I need to check that axiom I3 holds for this set I that I defined over there. Now, so I'm going to do it by induction again. I'm going to prove I3 by induction on R minus the size of J, where what is R? R is the size of the bases. Not the bases, they're not bases yet.
The elements.
Of the set in B. So I need to check axiom I3 for any pair I and J of independent of not independent sets. I and J in that collection script I that satisfy that I is smaller than J. And I'm going to do it by induction on R minus J. And again, so let me say 2A, base case. The base case is where R minus J is equal to 0. Okay. So that means J has size R, the maximal size among the things in B, and among the things in I. Okay. It's already in I, and it's maximal, so that means it's in B. Is that clear? Should I say that again?
What is J?
It's just some set not. Right?
So
Some set in.
remember, this is the statement that we're headed for.
Gotcha.
Yeah.
I don't blame you. There's a lot of things to keep track of here, definitely.
I'm not quite clear in that I have that all the sets in B have the same size, but I'm not clear yet that I have that all the sets that are the same size
Are actually
in B.
So let me say another word about this. J is equal to R. Now, by assumption, J is in my collection script I, which means by definition that it's inside a basis, inside a set in B. J is in I, therefore J is a subset of B for some B in B. That's the definition of script I. Okay. But now I can say, well, this guy has size R because R is the size of the sets in B. And this guy has size R by assumption. And therefore they're equal.
Yep.
because they're this one is a subset of this one. If they have the same size, then J is equal to B, and that's why I said that J is a basis.
Wait, we can't call it that yet.
J is a
It's in B.
keep talking to me when I do this. J is in B. Okay, good. So now it takes some skill to try to use these cameras. So if you see me walking funny, that's because I'm finally figuring out where the camera doesn't get confused if I stand. I always have to stand in the center of the board. So if I cover, if I'm not letting you see, then let me know. We're inside the base case, okay? And inside this base case, I'm going to have to. Let me first draw the situation that we have so far. Let me maybe say one more thing, okay? Before I continue. J is a basis. J is in B, okay? And I is in script I. So that means that I can't see this, huh? So J is in B. I just proved that here. And I is in script I, which by definition means that I is a subset of something in B. I is a subset of A for some A in B. And now I want to draw a little Venn diagram of my situation that I have here.
Is that a strict containment?
Yeah,
actually,
it has
This
to
is-
be.
the cardinality of I is less than the cardinality of J.
So it's less than the cardinality, right?
Be careful.
Yeah, that's right. So it has to be a strict containment because A has size R and I has size less than R, because the size of I is less than the size of J. But, right, so then I is actually strictly a subset of A. It cannot be equal because it doesn't have the right size to be equal. Okay? So my little Venn diagram, let's put some colors into this proof here. I have two sets of B. One of them is called J, and the other one is called A. So here's the Venn diagram of J and A. Right? And I tried to illustrate the fact that they have the same size, and therefore I drew these two circles of the same size. Okay. Now, I want to put I into this Venn diagram, but usually you see the third set in the Venn diagram like this. But I is a subset of A, so therefore I has to go over here. I is some subset of A that might intersect this part, might intersect this part, but it has to be inside. So that's my Venn diagram. Okay. And I'm keeping this down here, which is what we're trying to prove. Okay. So let me draw. So we're in this base case, and I'm going to consider three possibilities. Okay. The first possibility is that I can find an element in this little piece right here. Okay, so I'm going to consider this piece right here. the Venn diagram. Okay? And I'm going to assume that there's something in there. Let me say that A is in there. So what I'm assuming is that this guy, let me call this C. I'm assuming that C is not empty. I'm not claiming this, I'm assuming it. Okay. Assuming this, I want to show statement I3. So I say, okay, so let A be inside this piece C. So again, remember, I is this red thing over here. So what can you say about I union A?
Contained in A.
It's contained in A, right? This is J. I union A is contained in big A, and big A is in script B, and therefore I union A is one of the sets in I. Okay. And also, just by looking at the picture, you can see that A is an element of J minus I. Because look at it, A is inside J, and A is not inside I. So I started with I and J, and I showed that you can find A in J minus I, such that I union A is in script I. That's what I wanted to show. So if C is not empty, I'm fine. It's my first case. If I'm in that first case, then I don't have a problem. Remember, so far this is just the base case. I mean, I know it's kind of shocking that the base case should take us so much work, but it does. That's why I gave them these labels 2A1, because I want you to remember that this is the first step in the base case of step 2 of my 2A2. Draw another picture. This is A, this is J. This is I, and now I'm going to look at this other piece over here. We call this piece B, and I'm going to assume that that piece is non-empty. So again, if it's not empty, then that means there's something in there. A. Let A be in B. And now I'm going to show you that this implies I3 in this case. Okay. What am I going to say? I'm going to say, look, A and J are in B. Yeah? And you can see that in that board over there is J is in B, and in this board over here is A is in B. A and J are in B, which remember is why rhythm of the same size. A is an element of A, and it's not an element of J. So again, what I have to do is the only thing that I can do in this situation, which is to use exchange. So I can find another guy, which I'm going to call J. in J minus A such that big A minus A union J is, in my collection, B. J is in J minus A, so it's in this part of the picture over here. Here's J. A minus A union J is in B. Okay? Well, if you stare at this for a second, you're going to see
That I is contained in that. I is still contained because we took out A, which wasn't in I.
I mean, I is definitely contained in, right. I is contained in A minus little a. I is contained in A minus little a, because I had A over here and I just took out this element which doesn't involve I. So I is contained in A minus A. So if I add J to them, I union J is contained in A minus A union J. And this guy is in B. So this guy is a subset of a set in B. And therefore, I union J is in script I. And J is where I want it to be. J is inside J minus I. Why is that? Well, look at it. J is in J minus I. It's clear from the Venn diagram. So if this part B is not empty, then again, I'm done. Okay. So my third case is the negation of these two. Suppose that C is empty and B is empty. Let me draw my Venn diagram again. Here's J. Here's I. And you see, where is A? Well, there's nothing here, and there's nothing here. So actually, there's nothing here, and there's nothing here. So this is A. In other words, A is equal to I. If C is empty and B is empty, then I is equal to A. I can say it in symbols. A minus I is B union C. You see the picture and you see that A minus I is B union C. So if these two guys are empty, that means A is equal to I. But I'll remind you that Jeffrey pointed out that this is a strict containment. Strict. I had a strict containment here, which means that this cannot be true. Contradicting the strict containment I is contained in A and not equal to A. So that's 2A3. And that concludes my proof of 2A. Okay. It is long-winded. Definitely. It doesn't just seem like it. Okay. But I just completed 2A, the base case. Remember, this is the base case of I3. So what am I missing? I'm missing 2B which is the inductive step. Which a little bit surprisingly, it's actually shorter than the base case. But we ran out of time, and so I'll post that on the notes and make sure that you read the end of this proof and therefore the end of this theorem over here. I'm sorry? I'll also post the homework tonight or tomorrow. And again, as I said, the reason that I subdivided this proof into these little pieces is so you can look at the notes and maybe draw a map of what I just did, because I know it's complicated.
I realized when I started talking about bases that I hadn't actually written up the last part of 6.
So which part was?
The showing of Dick has actually once I said I felt so satisfied that I just stopped. I'm going to show that the bases are like, oh, I was supposed to say that.
Yeah, no,
So I mentioned one thing.
Okay, did he give you any ideas about where to
Yeah,
start?
we just talked to, well, I mean, I've already asked a few questions, so we can start from
Yeah, I just didn't know if maybe you said you jumped down.
I did mention
Yes, I'm actually not in a funny way because I only drink decaf.